Uh, Hello, this is Dr. Hussein in Electrical and Electronic Circuit Analysis in Module 2, where we are going to investigate single and three-phase circuit analysis. In the first week, the topic title will be AC Circuit Techniques and Analysis, where we are going to cover AC power calculation, how to calculate power in AC circuits. We know how to calculate it in DC, but let's see how to calculate it in AC. What are the different type of powers in AC circuits? Then after that we will discuss the reduction or simplification of electrical circuit using Thevenin and Norton equivalent circuits. We will go through the circuit operation waveform formula as we doing in this semester. And the third point, the maximum power transfer. We want to see what is the maximum power transfer from the supply to the load. How we calculate it. Is it similar to the DC circuits or it's different? This is what we will discuss. And finally is AC circuit techniques and analysis, where we use methods, techniques, approaches to analyze electrical circuits, as example mesh analysis, nodal voltage, current divider, and so on. Okay. Now after that we go to find the power. We mentioned in the module 1 that the power, okay, we are talking about single phase here, power is VRMS, IRMS, cosine the angle between them, which is already we have it. This is VRMS, this is IRMS, and this is the phase shift we already calculated. So this is the power. Which power? This, what we call it? Power could be general power, we call it. Sometimes we call it active power, or let me say real power. For the imaginary power, or the what we call it reactive power, which is power due to the imaginary elements like capacitor, inductance, again VRMS, IRMS, which we already have it, times sine the angle theta. Okay, so we just need to substitute. But remember, for power the unit is what? For reactive power the unit is var. Okay, now we want to see how much reactive power in inductance and in capacitors. Okay, it's similar to the calculation of power in DC, I square R, but here I square X L. Okay, for inductance, I square RMS, definitely we are dealing with RMS, XL. Do you remember what is XL represent? It's represent reactance, right? Also in ohm. So I just substitute and again in var my results. What about QC? QC is the current square times XC. XC is the reactance for what? For the capacitor. And IC square is the current RMS current in the capacitor, which is already given. Here I divided by, because I have the maximum, I divided by square root 2 to come up with the RMS. Okay? And don't forget the minus sign for X, because this will give minus reactive power. Okay? Reactive power be in minus sign, which means that capacitor, when it is negative, the reactive power, which means it's let me produce, it means inject reactive power to the circuit. While for inductance, because it is positive, it means it's absorb reactive power from the circuit. If I want to find the total reactive power of the circuit, then I need to add them. Algebraic addition, very simple algebraic addition, and this is positive. When it's positive, it means the circuit is inductive more than it's capacitive. I mean, the inductivity of the circuit is higher than the capacitivity of the circuits, so it's more inductive circuits. Okay. Now, what about the power delivered to the resistance? This is very similar to the DC circuits. I square R directly. Okay, we got it in watt. Don't forget reactive power in var, active power in watt or real power, and apparent power, it will be volt ampere. Now let's take example how we deal with power and the power triangles. See this example. He say find the power, reactive power, power factor for the source. Also find the phasor current I. For the source, okay, he want to see reactive and active power. Just a minute. Let me read the circuit first. The circuit, we have voltage source. Okay, we have two parallel elements. The total current I. Okay, divided into IA and IB, current following through load A and current following through load B. For each load, some information given, I will use this information to find the unknowns. As example, here in A we are given 10 kVA. Just a minute. K it's kilo, but VA, it means this is S apparent, right? S apparent. Okay, power factor is 0.5 leading. Now let me ask a question here. Leading, what does it mean? Is it capacitive or active? I'm sure you will say it is capacitive because current lead the voltage in the capacitive. Now the second dot B, I am given here 5 kilowatt. So this is power, right? This is power. This is P. Okay. Now the power factor is 0.7 lagging. So this means that this is reactive power. Reactive power. This is inductive. Okay, or inductive load. I will start from A. As you can see here, power factor is given 0.5. We say that this is capacitive. So capacitive, the reactive power will be negative, as we discussed before. So the triangle will go down, looking down. Okay. Now also he gave me S, which is VRMS, IRMS, which is 10 kilovolt ampere. If I have side and an angle of the triangle, I can find the other sides, right? So we can use mathematics to find the other sides. For load B, I also am given power, which is the horizontal. Usually power is the horizontal side, and I am given also the power factor, the angle. Okay, the vertical side represents the reactive power, and it's up, looking up, because this is inductive, not capacitive. Capacitive looking down. Okay, it means for inductive, this is how it look like, the triangle. For capacitive, it's looking down. Okay, now we start with load A. Load A is S given, which is VRMS, IRMS, and the angle cosine phi is given, so I can find the power. Very easy, multiplication. I have power, I have S. Can I find Q? Yes, because S square equal P square plus Q square. I have P square, I have S square. Let me find the Q. It's just merit of math. You see here, still negative. Okay, because it's capacitive load. Now theta B is the angle. Okay, our angle. Okay, I will take cosine inverse, then I will find theta B. Okay, for B. Now QB, this is just in case if I want, this is for B. For A is already done. I'm talking about now B, load B, which is the inductive load. So I found the angle theta, then Q is P over, because tan is opposite over adjacent. Okay, so we can find the Q. This is from mathematics, from trigonometrics. P tan theta. Theta I already got it, which is here. P is given to me in the question, just substitute to find the Q. If I have a Q and I have B, can I find S? Yes, because we have formula, as you can see here. Okay, now I have P, I have Q for each one of these loads. Then I will add P together, and I have a Q together. Then I go at P and the Q for the whole circuit, for the loads. Okay, now if I want to find theta, then tan inverse Q, the imaginary part of the real part, we go with the angle theta. We have volt ampere, which means the S of the circuit. We can have it because we have P and Q. We just substituted, we got S. Now VRMS is given in the question. It's 1414 over square root 2. We have RMS. What about IRMS? This is what I want. The total current, RMS current, is S, which is VRMS IRMS, over VRMS, which is already calculated here. We got the current. Okay, don't forget, we want to know the power factor also. Okay, the current of the circuit, coming from the supply, and its angle. Okay, now the current will be square root 2 IRMS, because I'm looking to the maximum. I want to represent at the end in time domain. So RMS current is here times square root 2. It gives me the current, the maximum current. What about theta I, current of angle of the for the current? It is the theta v minus the total theta. Theta v, I have it in the question given, and theta I already calculated. Where is it? This is somewhere here. Okay, I need to substitute to find theta for the current, because here the magnitude, here the angle, so I can't write it in the final form. Now this is the voltage, which is already given the question. This is the current, this is what we already calculated. Now I can sketch the phasor diagram. Have a look. The phase shift is, this is 49 point something, let me say 50, and this is 30. So from here to here 30, and from here to here 50, around 50, and the difference is 20. Okay, this is the phase shift between current and voltage as requested in the question. Now if we go to Thevenin simply, when we deal with circuit, let me say complicated circuit, have many items, many elements in the circuit, and at specific points, A, B points to terminal, we want to summarize, to simplify, to reduce the circuit into just supply in series with impedance, similar to the discussion last semester in DC circuits, but it was with the resistance. Here with impedance, as you can see here, this is called Thevenin equivalent circuit. It means I already selected points A, B. Here could be any load, anything, and I reduce the circuit to become just simple impedance in series with the supply. Easy. Now this supply, which is called V Thevenin, T for Thevenin, it's the open circuit voltage across the terminal. With example it will be more clear. What about Z Thevenin? Z Thevenin is V open circuit over I short circuit across the terminal. Okay, V open circuit already, V Thevenin, we define it, and this take me to say that I can also reduce between A and B the circuit to be supply current source in parallel with impedance, the same impedance. So Thevenin, the third Norton is the same. Okay, let me back here. Okay, now what I will do here, A, sorry, here A and here B. Okay, I will make a short circuit between them to calculate this short circuit. Okay, now this short circuit, because it is there, okay, the current when it comes to this is one node. All these represent one node. When the current coming here, it will not follow here. It will not follow here. Why? Because it will follow in the short circuit back. So the current IR represent current coming through supply, current source, and let's do this step by step. For the first part, which is Z Thevenin, we mentioned that we have 100 ohm in parallel with minus J 100 ohm. So this is Z Thevenin is 1 over 100 over plus 1 over minus J 100. Simplify, this is Cartesian, convert into polar, do the division, and then convert back into complex, which is in Cartesian. This is the real, this is the imaginary. Real is R, which is 50, minus J 50, which is the ZC, capacitive load. Now this is Z Thevenin, I got it. Now let's come to the short circuit current. I short circuit here plus IS here equal the current IR, because you see here it will come here, nothing will follow here, it will follow here, and this is following here, and then back, joining back. This is current Kirchhoff current rule. Okay, law. Now IR easy to find. Okay, IR, because it is VS IR, the current here is the potential difference between the voltages here and here divided by R. Here the voltage is 100, here the voltage is 0. Okay, so I divided by 100, it will give the IR. Okay, now IS is the source current, which is 1 with 90 is given here, as you can see. Now we can sabotage